Don't forget to check out the cool information and link for Altum Design software later in this video. Okay, here we are, and this is going to be our very first project, complete project that is. So what we're looking at here is an irrigation system, and we are simply going to program an Arduino to control 3 sensors in this case, and 1 relay, which is going to be the actuator, the relay, and the relay is actually going to be the one to control the solenoid valve. So let's first design what this should look like. So intuitively, if you're talking about irrigation, you're going to sense, analyze, and act according to our general automation model. And in sensing, we want to be able to sense light. We're going to do this using an LDR, a light-dependent resistor. We also want to be able to sense rain, actually. So we're going to be using a rain sensor. This detects actual falling raindrops. And we also want to actually detect how much humidity is in the soil. So how humid or moist is our soil, which would make us take the decision of irrigating. And we're going to use a soil moisture sensor for that, obviously. And we're going to analyze this data with our MCU, which is going to be our brain. And we are going to act on this data by actuating a solenoid valve, which we will control using a relay that we saw in one of the previous videos. Alright, so this is our model. This is what we're going to start off with. So this is what the wiring is going to look like in the end. This is the wiring that I used in this case for this project and this code, and it's down in the description, of course. And I used a software called Fritzing, which we will actually be looking into in the next video. We're going to look at quite a few software packages. Okay, so this is what we have, and we're going to start off with our microcontroller, an Uno, and let me get these guys out of the way because these are from previous videos. We won't be using these today, and we will use, of course, the breadboard. So let's start off with the sensing model, or the sensing part. This is an LDR, a light-dependent resistor. So it's a resistor which varies its resistance, if you will, depending on the amount of light that falls on it. So it has 2 legs. It's very simple. So we're going to just plug this in for now, and we'll look at the particular wiring in just a few minutes. This is our soil moisture sensor, and it's a sensor, and it comes with this little board, which is very easy to connect. It's simply a positive and a negative end over here, and it comes with its own 2 cables. And try to get these in here, okay. And the other ends of these cables go into the actual sensor. Okay, so much for our soil moisture sensor. Got it. Okay, so let's get this guy out of the way, and let's look at our second sensor, or third sensor rather. This is the raindrop sensor. So this is actually able to detect raindrops falling on it. So this will actually detect rain conditions, if it is raining or if it is not raining. The soil moisture sensor, on the other hand, is actually going to detect whether it has rained. So that's going to be how these 2 sensors complement each other. So if it has rained, then the soil moisture sensor will be able to detect that in the moist soil. But if it is raining, is something that's going to be detected by this raindrop sensor. Okay, and this is our actuator, the relay. The relay we saw is used as a mechanical switch, and it has a low side and a high side, and we will be actually connecting a solenoid valve, which is a 12-volt, actually, DC solenoid valve. So the high side is not going to be that high in this case. Normally they're used for 120 volt AC, which is for like lamps or compressors or even 240s and stuff like that. We're only going to be using 12 volts, and it's actually going to be DC, so it'll still work. So let's just wire the VCC and the ground and the signal pin onto our relay, and then we'll worry about the high side. And the high side is maybe kind of tricky, but we can actually kind of visualize the way it works, because what you want to do when you control something like a light switch that is used in a room to control a light, one of the cables is completely interrupted. So one of the cables from your light on your roof actually goes straight into your what's called the live wire, and the other terminal from the lamp is actually interrupted by the switch. So it's very easy to conceptualize or to visualize the fact that one of the wires is constantly connected to the power and the other one is not, and therefore the lamp is unable to turn on because it's kind of like there's no bridge to close the circuit. So we will be doing exactly that with the relay. The relay is going to help us close that gap so that we can complete the circuit and light what we want to, which in this case is going to be a solenoid. Okay, so let me get the VCC ground and signal pins for the raindrop sensor. Again, most of these sensors have 3 cables to them. The 2 power cables and the actual signal cable. And the same goes for the soil moisture sensor. So it's got 1 VCC, it's got 1 ground, which in this case I ran out of black wire, so I'm going to use a green one, and it has 1 signal. Okay, so we have our 2 the soil moisture and the rain sensor wired up, and let's get the power jumpers connected to the power rails of our breadboard. So there's the first sensor connection right there. Okay, and we're just going to leave the signal cable plugged into the breadboard somewhere right there, just to keep the wires in order. And now the rain sensor. So the same goes for the rain sensor. We're just going to plug the power cables into the rail down here, and the signal cable is somewhere on the board right there. Okay. Now the light dependent resistor, we're going to move over to this same side of the board, and we're going to wire this up in a minute. Let's get the relay wired up. It's going to go over on this side. It's closer to this power rail. Plus and negative right there. And the signal, we're going to plug it into the board. So these signal cables are just randomly on the board right now. That's not exactly where they're going to go. So let's bring in the microcontroller. And as we are connecting these, let's just think about what needs to happen. The microcontroller needs to supply power, but it will only supply power to the low power consumers. So here's the 5 volt coming out of the microcontroller. It always has 5 volts. And here's the ground. So it needs to go to the rails so that it'll power the raindrop sensor and the soil moisture sensor as well, and eventually the light dependent resistor. Right there. These are all sensors with low power consumption. Okay, so they can be powered from a microcontroller. Okay, and we are also going to take ground to the other side of the breadboard, to the other power rails. We will be using a separate power source for the solenoid valve, because solenoids, in this case, this requires a 12 volt power source. Okay, so here we're wiring up the LDR, so it takes a positive on one of its legs, and it also takes a signal and a ground connection from the other leg. So the other leg of the LDR is going to connect through a resistor directly to ground, as I did right there. And the same pin also connects to the actual signal pin that we want on the microcontroller. So again, this can get kind of complicated, but the wiring instructions are on the diagram. So the signal pin from the LDR goes to one of the analog pins. And since we're already wiring data pins or signal pins onto the controller, let's bring in the signal pin from the soil moisture sensor, and let's bring in the signal pin or signal cable from the raindrop sensor onto the microcontroller. So we have pins A0, A1, and A2 connected, and now we're going to connect the signal pin to the relay onto pin 7 on the other side of the board. So our relay is also ready to operate. And the last thing we need to bring in is the solenoid valve. So the solenoid valve, which is the last component, has two cables to it, as you can see right here. And what we're going to do here is what really should be quite intuitive. So one of these cables is going to go from the power source to one of the terminals, which is labeled normally open. So it means that that terminal on the relay is normally open. It might not seem so intuitive if you say it that way, but normally open means that it is not normally closed, which means that the circuit is not normally closed or completed, which means that if you plug it in that terminal, it will not receive power at the start. The other cable goes out of the common terminal, which is labeled with the letter C, directly to the solenoid. So we took VCC, which is going to be 12 volts, through the relay into the normally open and out the common into one of the cables of the solenoid. The other cable from the solenoid is going to go straight to ground. Now remember, the VCC going into the relay and into the solenoid through that normally open and common terminals is not going to be 5 volts coming from our Arduino. It's going to be an external power source, which in this case has to be 12 volts. And that is what we're going to use to power the solenoid. So on this other side of the breadboard, the power rails actually contain 12 volts, not 5 volts. So although VCC is different on the top, it's 12 volts positive, on the bottom it's 5 volts positive. Okay, we're going to move the relay power cables that were on that side to the 5 volt, because we need to feed 5 volts to control the relay. We only need 12 volts to power the actual solenoid. So 5 volts down here to power our sensors, LDRs, and the relay low side coming from the Uno, and 12 volts on the other rail coming from the battery pack and into the solenoid. However, even though 5 volts and 12 volts are different on both sides of the breadboard, the ground is actually interconnected. So the grounds need to be connected. So let's actually connect the common ground between one power rail ground and the other power rail ground in this manner. And now both grounds are connected, which means that both sides are actually 0 volts. and the high side is 12 volts greater than 0, and the low side is 5 volts greater than 0. Okay, so we are now ready to test our project. And we're going to use this, make sure that it's set to 12 volts. Yes, it is. And we are ready to test the code. So let's look over the wiring one more time, and then look at the code and run it. Okay, so here is the wiring one last time. And all the sensors go to A0 is the raindrop sensor, A1 is the moisture sensor, and A2 is the LDR. Okay, this is the code. All we're going to do is send high and then low to the pin number 7, which is where the relay is connected, with a 2-second difference. And we're only going to run this once, which is why it's in the setup function. And here it is. Resetting the MCU, and look at the relay. LED turns on, and 2 seconds later it turns off. Okay, so let me introduce Altum Designer. Why? Because we're building all these projects and the idea is to make a product we can sell. After all, the only thing more satisfying than a working Arduino project is a profitable one. Nowadays you can have your prototype or final designs printed by a professional PCB service. All you have to do then is make a cool case for it, slap your logo, and ship your products. Altum is a software that lets you drag and drop your designs onto a graphical user interface and automatically route all the connections for you and even send it off to get printed. Whether you're a freelance designer or part of a multi-company team, Altium has you covered with electronic and mechanical design, online collaboration, and even connection to manufacturing. Altium is the most trusted PCB design system with over 35 years of innovation and development. So when you're ready to make some serious money, Altium takes you from the idea to product faster and without the hassle. Download a free demo and try it today. Use the link in the description below for this video. Okay, so let's work on the final code. So the first thing we want to do is we want to create variables for the light, rain, and humidity conditions and set them to 0. And then we're going to create the variable pins, or the pin variables, for each one of the sensors and for the solenoid pin. And then in the setup, the only thing we want to do is set the solenoid pin to output mode, just to make sure that there's nothing coming in through there. And then we are going to do, the first thing is establish a baseline. So in our loop, we will write the values of the analog read of each one of the 3 sensors to our variables and print them out to the serial monitor. So let's go ahead and upload that code and take a look at the serial monitor. And there it is. So what are we getting? We're getting rain value of 0, humidity somewhere between 55 and 58, light conditions between 55 and 58, and humidity is all the way up to 99 or 100. So what we want to do is we want to take these baseline values, and we know that right now these sensors are not dipped in water, there's no rain falling on the rain sensor, the light falling on the light sensor is basically normal interior light conditions, and humidity is dry because the soil moisture sensor is dry right now. So let's go ahead and throw this logic into our loop function. So once we print out the values, we're going to go ahead and work through this logic. So what do we know? Well, we know that a rain sensor gives a value of 0. So if the rain sensor is, in this case, below 10, so I made it a little bit more stringent, then it is not raining, which is clearly the case right now. And let's go ahead and add or nest in a second if. So we know it's not raining. So what else can we do? Well, if the humidity is greater than 70, which is indeed the case right now when the soil moisture sensor is dry, and the light conditions are greater than 70 as well, which, as you saw right now, the interior light conditions are 58. So out in the field, if it's going to be very dry due to due to sunny conditions, then light is probably going to be greater than 58. So if those two conditions are met, then go ahead to the next set of commands, which is digital write high to the solenoid pin. And the solenoid pin, as you recall, will open our valve and let the water through and irrigate. So we are basically checking for 3 conditions. If there is no rain, which there isn't, if there is humidity, in this case greater than 70, which is counterintuitive, but you can just flip the cables around or adjust your pot on that. And if the light is greater than 70, then it's a very dry condition. So we will definitely want to irrigate. All right, so this is what the first set of ifs does. Then, if the rain value is not less than -10, or if it's not that low, then it is probably raining. And if it is raining, we don't need to check for anything else. If it's raining, we simply don't irrigate because there's no need for water. All right, so let's go ahead and I'm going to finish commenting this code here, and then we're going to upload this, and we'll go ahead and take this to the field and give it a first try. All right, see you there. All right, so here we are outside, and I've got the setup just as we talked. And the only thing I've done is I removed the LDR, as you can see, because once this LDR is in place, all three conditions are met, which means that the relay will activate and water will begin to flow, which is not what we want from the get-go. So I don't know if you can see the LED in these highlight conditions, but let's go ahead and move the LDR into place. And there it is. It is now in place, and so all three conditions are being met, and the LED on the relay is now on, as you can see. And this means that the solenoid connected to the relay has been activated. Now, the solenoid is hard to check on, so you can sort of feel when it is activated, because it has a small bump or click in it. And there it is. Here's the water irrigating as expected. And if for some reason it became dark at this time, for example, and there's no more need for irrigation, it would be equivalent to removing the LDR, which I just did, and the solenoid closes, and irrigation stops. All right, great. So this is what we were expecting. There's a lot of tweaking to be done before this can actually become a viable product. Okay, so this is our final project, and if we would want to turn this into a viable product, we would need to build a casing for it. We would need to tweak a little bit or mess around a little bit with the parameters. Make sure that, like I said, everything turns on exactly at the moment that we want it to turn on. We also have to look out for conditions where something we're not expecting happens. And we need to make sure that we consider a lot of the possible alternatives, which has to do with user experience. All right, so that's pretty much the complete project. We went from sensing to analyzing all the way to acting, and this is basically the model that we would want to follow for any future projects. So I hope you guys enjoyed this, and don't forget to share, like, and subscribe. See ya.